Welcome everybody to the online seminar series Machine Learning Needs Mathematical Optimization. We have the pleasure today of having Professor Martens from the University of Antwerp. He is a professor of data science at the Department of Engineering Management. David defended his PhD dissertation in 2008 at the Katholieke Universiteit Leuven. And then he was a visiting professor at the Stern School of Business at New York University. Since 2010, he is the director of the Applied Data Mining Research Group at the Faculty of Business and Economics at the University of Antwerp. In his work, David has collaborated with large banks, insurance companies, telco companies, as well as with various technology startups. And he has received funding, for instance, from the AXA group to study explainable artificial intelligence applied to the insurance companies. In his research, he has published in high-impact journals such as European Journal of Operational Research, MIS Quarterly, International Journal of Forecasting, and Decision Support Systems. He's currently the senior editor of the Informed Journal on Data Science. Today he will be talking about counterfactual explanations. At the very end, David will also show us a book that has just come out about data science and ethics. So with all of this, we are extremely happy to have you here today, David, and the floor is yours.
Okay, thank you, Dolores. And so when I defended in 2010, Dolores was member of my PhD committee. So I'm very happy to present to you again, Dolores. So today I'll talk about the counterfactual explanation, and so how this can be used to explain these ever more complicated prediction models that we've been using in artificial intelligence. And the irony is that in order to explain these complicated models, we're throwing yet more complex algorithms at the problem as a solution. And so I'll talk a bit of why we do this and whether we should actually be doing this. So, but let me start with a story. So a couple of years ago, in 2019, there was this famous tech entrepreneur who went to Twitter and he said, like, my wife and I, we both applied for an Apple card. And even though we share all assets, my wife got 20 times less credit limits than I did. And he claimed it was sexist. It's simply because of the gender. And interestingly enough, he said, my wife spoke to 2 Apple representatives. They were very nice. And they said, well, but I swear we're not discriminating. It's just the algorithm. And so this is very recent, where clearly a black box model was used to do credit scoring by Apple. And because of that, lots of uproar and sexist allegations. And even more, Steve Wozniak, the co-founder of Apple, said the same thing happened to me. It's big tech in 2019. And because of all of this, there was even a formal complaint being filed in New York against Goldman Sachs, who is doing the credit scoring for Apple cards. And so I'll come back to this exact story at the end, where my claim is a bit that this is not so much about discrimination, but much more about being able to explain these decisions. So what's going on here? Why? How can these kind of things happen in our current society? So I think all of us know that the major advances these days in predictive modeling is deep learning. We've seen definitely in image recognition that deep learning has really blown away all competition. For example, you have these kind of papers that do use deep learning for diagnosing skin lesions as malignant or benign, working better than dermatologists. Superhuman speech machines, so speech recognition, already in 1999, they claimed that you had these deep neural networks that are better than humans in recognizing speech. Deep mind in bioinformatics. Very recently also, Google unveiled deep learning where you give a picture and it will predict the location of that picture pretty accurately. So many applications, and all of that is mainly spurred by deep learning. So what's the issue with deep learning? It's a huge neural network. And when I say huge, it is really big. So for example, the mobile nets model, which you can download yourself, it's from Google, and it's used for image recognition, I think, in about 1,000 categories. Well, it has 4.3 million parameters. So if you would simply print out the formula of going from an image to one of these categories, you would need a book that's thicker than the golden pages or thicker than the Bible. And so, of course, people understand how deep learning works, but this one formula, this one model, try to understand how you go from some pixels to a final categorization with this huge book. It's nearly impossible. And then we're not speaking of GPT-4, for example, when we talk about text. This one has 100 trillion parameters. So actually very complex models. But then you might argue, well, but deep learning is great for images and text, but I'm working with regular data. And so we just use the traditional approaches. Well, but even then, random forest, or in here, I just wrote the formula of an RBF kernel SVM. They are also very complicated. So you have here this function with hundreds of terms, and every term is an exponential function with as many dimensions as you have dimensions in your data. So this as well is very, very complicated to understand how you go from inputs to a final output. And another argument might be, well, but I use a linear model, so I don't have this issue. Well, it depends on the dimensionality of your data. And definitely if you work with textual data or behavioral data, often you have hundreds, thousands, even millions of dimensions. And then looking at the top coefficients, which is typically done in a linear model, let's look at the variables with the highest coefficient. That doesn't work as well either. So I give an example here from the famous study by Kosinski et al., who used Facebook likes to predict a whole bunch of personality traits. And one of them is predicting whether you have a high IQ or not. And here on the left, you can see the top 10 Facebook pages with the highest coefficient in this linear model. So most predictive to have a high IQ. And so it relates to humor, science. Okay, makes sense. But this doesn't explain the predictions of most people. Most people that have a high IQ would not have liked any of these 10 pages. Because being predicted as a high IQ can also depend on hundreds, thousands of other Facebook pages which also have a positive coefficient. So these kind of explanations are very, very limited. So these days we see we have complex AI models that are creeping into our lives, and not just deep learning, also elsewhere. And explaining these decisions is really extremely difficult. And so do we need explanations? Well, we really do. There's few applications that you can think of where you do not want some explanation for some decision or prediction that's made. For example, image recognition with this medical diagnosis, and I'll come back to this. If an AI system says, well, we predict there's cancer here, the doctor would like to know, why do you think that's the case? But even in something with little human impact as Industry 4.0, let's say predictive maintenance, predict when a machine will break down. And if the AI says, well, the coming day, that machine will break down. Well, likely the operator would like to know, well, why do you think so? Because last week I already maintained it. And so just saying it will break down will do little for this maintenance guy who needs to work on a machine. And definitely in many other areas, explanations are needed. So, but why do we need explanations? So we agree, often they're interesting, we would like to want to have them. And the consensus in literature is that we all want them for trust, whatever trust means. So I'd like to look it up in the dictionary then. It's a firm belief in the truth of something. So when we talk about trusting a model, we want to make sure that the true pattern is learned by this model. It's not some artifact based on bias in the data or something. And so typically we evaluate this. Did we learn the right pattern, we as data scientists, by looking at the AUC or the test accuracy on a test set. But this is just a proxy on your test data. And there are plenty of examples, and I'll give a few in a second, that show that having a good performance on your test set does not imply that it will work well on real life deployment. So those cases really ask for additional explanations for predictions, not just a summary metric that says it will work accurately in 90% of the cases. And so, although explainable AI is rather recent, research in this area, comprehensible data mining, has been around for a long time. And already Kayande, for example, in 2009, they said that even when models are known to improve the performance over not using these black box models, users will be reluctant to use them if they do not understand how the model works. And so this really has been consistently shown whenever you deploy these kind of systems. And also examples, so having a good performance on your test set does not imply you'll have a good performance in real life. And so let me come back to this application of, of image recognition for medical diagnosis. So you have an image of a skin lesion, and the prediction model will try to predict, is it malignant or benign? Well, in this paper in Nature, which has, of a couple of years ago, it has many thousands of citations, and they show how this deep learning model matched the accuracy of a team of 21 dermatologists on a test set. And so it seemed to work really well, why it's a Nature publication, and the reason also why it led to so many citations. But then the same authors, a bit later, they revealed that most of the images of the skin lesions they had in their data set, of the skin lesions that were malignant, often had a ruler in the image, as you can see here and here. And so not all images. And so the reason is that whenever a dermatologist feels skeptical, thinks there might be something wrong with the skin lesion, the dermatologist will add a ruler to the image, just for future reference to see how large it is. And so if you don't give an explanation, then perhaps the deep learning model simply has learned if there is a ruler in this image, then the skin lesion is malignant. And of course, in the test sets, you had the same issue. You also had the ruler in most images that are malignant. And so the test accuracy is not sufficient to make sure that you found a true pattern and that you didn't simply have this bias in your data set. If you would be able to give an explanation to this classification and say, well, because of this area or this kind of shape or the color or whatever it is, then you would understand, okay, I trust it. But if the explanation would be because of this ruler I see in the image, that's why I say it's malignant, then immediately it's revealed, well, the model has learned the wrong thing. The model, this formula thicker than the golden pages, very complex, but clearly it focused on the wrong thing. And of course, that paper where they revealed this didn't get that many citations. That's the first one. Then there's this other famous story where they use image recognition, deep learning to predict when you have a picture of a tank, whether that tank is friendly or enemy. And in this story, it goes that the performance is great on the test sets, but if they deployed it in the field, it worked very badly. And then it was revealed that, well, all the pictures of friendly tanks were taken during the day, and all the pictures of enemy tanks were taken during overcast days. So probably what the deep learning model has learned, if there's background that's sunny, then it's probably friendly, and otherwise it's enemy tank. So again, if you just assess on the test set, you would not have revealed this issue that occurred. You would have a terrible model if you would deploy it. But even though this story is told quite often, somebody investigated what it actually is true, and apparently it's not. It probably never happened, so don't tell this story anymore. Plenty of other stories, but I have to tell this story to convey you not to tell this story anymore in the future. Another famous example, predicting whether an image has a horse in it, and the reason was simply because of this copyright symbol at the bottom, where most images of horses all came from the same person and all had this watermark in it. And so again, without an explanation, it wasn't revealed that the high accuracy on the test set was simply because the model has picked up on this watermark. So explanations are really needed if you want to trust AI. We cannot rely on simply the test accuracy if we're using very complicated models. So we really need explanations in that case. And then there was some discussion in the field. Well, do we really need to explain these complex models, or should we move towards more explainable, very interpretable AI itself? And so there's this one paper by Cynthia Rudin who says stop explaining black box machine learning models and start using interpretal models instead. And so she claims that all these complicated models, you might as well use a model that's slightly less accurate, but much more comprehensible. And that's much better. And so we should all focus more on such kind of AI that's interpretable by default and not these post hoc explainable AI algorithms that we put on top of complex algorithms. However, whenever you look at image data, speech data, there really is nothing better by far than this complicated deep learning. So even though the idea is great, currently I don't see much research that can do what these just very complicated deep learning models can do. But then on tabular data, we were kind of surprised that there was no empirical study ever done to show this. Do black box models actually perform much better than white box models or not? There's been some papers that do benchmarking papers in one field, like in credit scoring or in software engineering or in certain churn prediction, but nothing overall. And so a PhD student of mine, Sophie, she did a large benchmarking study on 90 data sets. And she looked at exactly that. What if we apply some black box models, but also white box models? Do the black box models consistently perform better than the white box models? And well, actually, indeed, in the majority of the cases, the black box model performs significantly better than the white box model. So here you can see with the significance test, you see the random forest, black box, SVM, the neural network, they all perform significantly better than these white box models we included. And so for 70% of the data sets, the black box model performs better than the white box model. But, and there's a very big nuance to be made. For the majority of the cases, this difference is rather small. So what's shown on this graph? Well, on the y-axis, you see the difference between the performance of the black box and the white box model. So the higher the value, the better the black box model is compared to the white box. And on the x-axis, it's simply ranked for all 90 data sets. And so if it's 0, so that's a black line, it means that the white box and the black box perform just as well. And so everything above the line means the black box model is better. And so in 70% of the cases, the black box model indeed is better. But you see, for most data sets, it's actually quite close to this 0. So, and only for a few data sets, it's really much, much better. And interestingly enough, for some data sets, the white box model performs much better than the black box model. But typically, these are toy data sets like tic-tac-toe, which you can easily summarize in simple rules and much harder in mathematical formula. And so if you have these opaque data sets, we call them, data sets where the black box model works much better, then of course it's worthwhile to use these black box models at the expense of lower comprehensibility. But the idea is that you should really look whether the black box model actually performs better. And so simple models often work well too, and if so, use these. Okay, and then we go to explanations. So explaining these predictions, and we focus specifically on explaining individual predictions. So tell me why my credit was being rejected. And why do we do this? Well, most often we're interested in explanations for individual instances. For example, a person of a bank asking, why did you reject my credit? Or why did you reject my, I applied for a job, why do you not send me an offer? Or for a website, why do you classify this website as being adult content and so none of the ads are appearing there? Or why is this machine going to break down? So global models, they try to explain the black box model on the complete training set. And so either they're way too complex, so you have a decision tree with hundreds, thousands of nodes even, so they're very complex, they're black box by themselves, or they're quite small, but then they explain only a limited part of your instances. And so the most interesting cases we see over and over again in applications is really that you want to explain individual instances. And then the main approaches currently are either feature importance methods or counterfactuals. And so feature importance methods I think these are the most famous in data science, like Lime and Shap. And they briefly summarize, they make a linear approximation of the black box model around the instance that you need to explain. And then the coefficients of this linear model, these are then the explanations for your prediction. While counterfactuals, there's something different. They tell you what is the minimal set of evidence that's present in your data that needs to change. And if you would change that, then the class prediction changes. And I'll give some examples in a second. And so here, for example, is SAM. You have a prediction model that tries to predict gender. Let's try to predict gender based on all the movies you watched. Let's say Netflix wants to do this for some reason. And we have this user, Sam, and Sam watched 120 movies on Netflix, and Sam is predicted to be a man. Now, there are two approaches to explain this individual prediction. One is this evidence counterfactual, and that will say, well, if Sam would not have watched these 6 movies, Taxi Driver, The Dark Knight, and so on, well, if you would remove those 6 movies from the instance of Sam, then the class would change from male to female. So we say this is the reason why Sam was classified to be a man. And so a bit more formal, the definition is what is the set of evidence present in the data instance, where if you would remove that evidence, then the class change. And this evidence is irreducible. So if you would only remove 5 of these movies, any 5 of them, then the class would still not change. You really need to remove all 6 of them, and then the class changes. And then these feature importance methods, they give you results like this, where you say how many features you want. Well, give me the 10 most important ones. And then these are shown like this. The 10 features with the highest absolute value in coefficient in this linear approximation are shown. And you see Die Hard, Mission Impossible, and so on are shown. But also because they show the features with the highest coefficient in absolute value, some features that actually are pointing towards the other direction, like Stop Making Sense, apparently is predicted for being a woman rather than a man. And there are many issues with this. For example, you need to say what K is. It's not very fast, not very stable, and so on. But maybe most important, it's not guaranteed to be a counterfactual. And so if you would remove those first 6 movies of the line, it might be that you're still predicted to be a man. And so it's not necessary nor sufficient to be a counterfactual if these features end up in a feature importance method. Yet these are most popular with data scientists. There are 2 reasons. One I'll give in a second. But the secondary reason is, I think, because they have such great tools, great libraries, great marketing around all of this, and very nice visualization immediately of what the most important features are. And so in the very first paper that we did when we worked on this in 2011, and it got finally published in 2014, we worked on a case where we worked with a company in New York together with Foster, and this company, their business was, can we predict for a website whether it contains adult content or hate speech or not? And the reason behind it was that you don't want ads to appear on adult content, porn pages, or hate speech pages. And so they built a predictive model where for any website, based on the words on there, it predicts adult content or not. But some websites were, of course, wrongly predicted to be adult content, and you want to know why. And so that's where we came up with this idea of what is a minimal set of words. If you would remove it from the website, then the class changes. And so here is one of the very first explanations we saw. For example, if the site would not have the words welcome, bikini, and 18, then the class would change from adult to non-adult content. And then you notice, okay, many adult content pages on the first page have words like welcome. By continuing, you can confirm that you're 18 years or older. And so that's a pattern that was picked up. And so this swimsuit wear website wrongly got classified as adult because of these couple of words. We also worked with the European Central Bank. They come out every quarter with these statements and they want to predict, will the market predict that the interest rates will go up or down? And then, of course, you would like to know, well, why does the market think the interest rates would go up? And then we get these explanations like, if the statement would not have these words, upward pressure, vigilant, food prices, then the prediction would change to dovish. So if the intention of the statement is actually dovish, then this provides a guidance to say, well, these words might be wrongly interpreted according to our prediction model, so change these words to something else. And then we did a study, the same thing with Facebook likes. Why am I being predicted to have a left-leaning political preference based on my Facebook likes? And an explanation could be, well, if you would not have liked Greenpeace, Radiohead, and Climate March, then the prediction would change. And so this is an explanation for a real-life instance of somebody who was predicted to be a left-wing political preference. So many use cases around this where these counterfactuals really tell you what needs to change in order to come to another classification. And so the counterfactual, where it's key is that it explains a decision made by a prediction model on a single instance. And this combination of these three is unique in the explainable AI research, because the feature importance, they don't explain decision, they explain a prediction score. And for example, Lime will build a regression model that tries to mimic how the black box model makes its predictions around the instance to be explained. And so it's a linear regression model, and it's regressed on the prediction scores of the black box model. So it explains prediction scores, not decisions. And so another reason why data scientists love feature importance so much, because they're of course interested in explaining prediction scores. Because decisions, it's a combination of a prediction score and a threshold. And we know this threshold might change due to changing context. For example, a bank might say, I want to be more conservative because now we have this COVID situation. So I'm lowering my threshold before I give credit, even though the model itself remains the same, but then the decisions change. And so if you really want to explain the decision rather than the prediction score, automatically you really need a counterfactual. And so the other advantages to the counterfactual, for example, it provides a concrete justification. It seems to comply with GDPR on this matter, where you need to provide insight into the logic involved if you have automated decision making. It's stable, it's fast, few assumptions typically, and so on. And so key is that counterfactual explain a decision of a model for an instance. Then, okay, so wait a minute, we're going to explain these complicated models by creating yet more complicated models, algorithms that try to find this optimization. And so finding an explanation, it's an optimization problem. Okay, that's weird. That's really ironic. And then on top of that, the problem is incredibly ill-defined. And some people of you that are listening might say, well, the definition of counterfactual that I've seen is slightly different. I'm totally sure it's the case. And the reason is because it's so ill-defined. There's so many measures to evaluate counterfactual explanations. Some say it should be really short. Some say the counterfactual, the change should be minimal, which is not always the same as being short. Others, like Microsoft, says you should give several explanations, and these explanations should be as diverse as possible. An explanation should be actionable. And you could say, well, if your job would be in that area, then you get a credit. That's actionable. Another explanation could be, well, if your gender changes, then you would get credit. Well, that's not actionable. Feasible, plausible, justified, fast, so many other things. And really, this is just a selection of all these measures that are out there. It's really a big mess right now in the research, which is great for all of us researchers because it opens up lots of opportunities to do research in this and to understand what are now really the measures we really need for what kind of applications. And so there was a survey by Karimi et al. In 2021, which lists all these counterfactual generating methods. And we're very proud that we're the first one on this in this table with our ZC methods. And you can see that in these 7 years, more than 60 algorithms have been proposed. Incredible. Most of these algorithms, by the way, are published on arXiv only. And I think that's just another issue in research in general, with very, very bad code and very little benchmarking with other techniques that are currently out there. But you can see here that they're very different in terms of for what models are they applicable, only for neural networks, only for random forest, or for any kind of techniques or not. Do they include certain kind of constraints? Are they applicable to image data, textual data, or tabular data? What kind of optimization solution is it? Is it some heuristic approach, or what else do they use, and so on? So we thought, let's do a benchmarking study. There's so many of these techniques out there. Let's do a benchmarking study of the most important counterfactual generating techniques. And we focused on the ones where there is some code available. That already was surprisingly enough a huge endeavor, because the code that's out there is such a mess. But okay, we came up with these 10 techniques that we benchmarked with one another. And then we tried it on, I think, about 6 different techniques. And here you can see the 6 different metrics, sorry. And here you can see the results on coverage. And so coverage tells us how many of the instances that we want to have explained, for how many of them do we actually get an explanation. Because interestingly enough, many of these algorithms often do not find any solution at all. And if we look at the bottom left graph, if we look at all possible data sets with both continuous data, discrete data, or the combination, we see that the best technique generates only counterfactuals in 90% of the cases. So 10% of the cases, you simply have no explanation that's being provided. Of course, this in most applications is totally unacceptable. And suppose you're a bank and you say, well, sorry, you're one of the 10 customers we don't have an explanation for. But maybe you can come back again next month and maybe we have an explanation then. Of course, totally not acceptable. And this is just on coverage. And so here on the left, you see that for the different techniques, where each column corresponds to a technique, we looked at 5 metrics: coverage, sparsity, so how short is the explanation, how near is explanation in L2 distance, and so on. And we do the ranking over all the data sets that we included. And so the lower the ranking, the better. And briefly summarized, the results in gray are the best results. And so there's a tendency to see that CADEX, growing spheres, set C, that they perform quite well overall. But as you can see as well, it really depends on the metric you're evaluating. Depending on the metric, but also the data sets, whether you have only continuous, only discrete, or a mix of data sets, the results change as well. And so we try to summarize this. What technique should you use when in a table? And we were hoping to make it much more clear, these guidelines, but we had to make this kind of large table which explains what technique to use under what situation. And so CADEX seems to work quite well, but CADEX can only be applied if you have differentiable models. And so it only works with neural networks, for example. If you have random forest, it doesn't work. And so each of these techniques have these drawbacks, where constraints and limitations, and it works well on certain metrics, but not others. And so that spurred some other research that another PhD student of mine did, is can we find a counterfactual generating method that simply provides an explanation always? Because that seems to be the minimal acceptance criteria in practice. And that leads to an algorithm, NICE, nearest instance counterfactual explanation. And the idea is a bit the following. You have an instance whose classification you want to explain. Well, the idea is look for the nearest neighbor in your data set with a different class, and that's correctly classified. Because that will by default be a counterfactual. And so the difference between these 2 points is then the explanation. What needs to change in order to come to a prediction with a different class? And so here in the figure, you can see 3 potential counterfactuals, 1, 2, and 3. And so if you want the nearest, so the least that needs to change in order to come to a counterfactual, we would say, well, I would argue to choose the nearest instance number 2. But if you say I want it very sparse, I only want to change as few variables as possible, well, then possibly counterfactual 1 would be the most interesting. Even though the difference is larger, you only need to change one variable. And here you can see the difference between optimizing for sparsity or proximity. And so the idea is first find the nearest neighbor of opposite class that's correctly classified. Let's say it's number 2. And then we're going to optimize further in this area between the instance you want to explain and the counterfactual 2 in this case. And then in that space, we use a depth first approach where we say, let's start changing features and let's see when we have an optimal solution in terms of whatever you want to optimize. And so indeed, this approach has a coverage of 100% because it's very easy to find a nearest neighbor of the opposite class that's correctly classified. That's plenty of algorithms have been proposed that can be done very fast. And then in whatever time period that's left, you can optimize it further for whatever metric. And so we benchmarked it on 10 data sets with 2 black box models, both a neural network, but also a non-differentiable black box model, random forest. And then for each data set, we explained 1,000 different tests classifications. And then we found, well, the coverage, as you can see, is always 100%. So that's really great. And then we compared it to some other techniques that are kind of based on similarity as well. The what if tool of Google, a case-based reasoning approach, SetC and CF Proto. And we see that only our approaches and then the what if tool of Google, 100% coverage. But if you look at how fast it is, the nice approach, it's always around 1 second, or in the best case, not even 100 milliseconds. And all of these experiments are done on a traditional laptop. While if you go to this more advanced technique like CF Proto, it has a coverage of only 73%, which is really low. And it takes a long, long time, often even up to hours, to get an explanation. And then we have several approaches where we optimize for different things. And so that's also our message to the field. If you want to have counterfactual explanations that are really short, well, then optimize for sparsity in your algorithm yourself. And so that's nice, sparse. If you just want counterfactuals that are as close as possible, so the smallest change possible, well, then optimize for proximity. And indeed, you notice that if you optimize for proximity, the second column, then indeed you have the best performance in terms of proximity, of course. And the same if you optimize for sparsity or plausibility, and then you just consistently do better than whatever's out there. So it's really fast. It always provides an explanation. And what's nice is that you can say what you want to optimize for. But even that's really focused on coverage, really. Having fast, it's what you want in practice, fast, and you want an explanation always. But then even if you are making to that phase, there's still so many other metrics that you can optimize for. And so what it should look like is really ill-defined and an open research question. And then what's really interesting about counterfactuals is that it explains decisions. So I already pointed to that. It's the main reason why it's different from feature importance methods. And so why is that so interesting? Well, most of the time where we need an explanation, we want to explain decisions. And the first is whenever we have negative high stakes outcome. For example, my credit is denied. Well, then I want a counterfactual explanation. Because I want to know what needs to change in order to get a positive decision. Or I'm being rejected for a job offer. Or I'm predicted to have a high risk of recidivism and I'm being thrown back into jail. Well, tell me why. What needs to change in order to come to another decision? I don't want to explain the score, I want to explain the decision. And so we did a study with end users on Amazon Mechanical Turk, where we tried to see what users actually want. Feature importance or counterfactuals. And it seemed that definitely if it's high stakes and negative outcome, then they really want counterfactual explanations. But also when there's misclassifications, I explain something wrong. So that's a decision. It's not a score that you want to explain. Or a classification that's seemingly unfair. And so in these two cases, I'll explain a bit more how these counterfactuals really can spur the field even more. And so in this very first paper that we talked about, we already point to this. And so we explained the classifications of websites that were seemingly misclassified as adult content. And so this model that we built misclassified web pages, and then we say explain these misclassifications. And so in these first three websites, you see the counterfactual explanations. So what words would need to be removed from the website in order to come to a classification non-adult content. And I'm not going to read out loud the explanation, because clearly you see these three documents, these three websites were adult content. They are porn websites. And here we have an issue with the labeling that's wrong. So the prediction was clearly right, but the label was wrong. And so this explanation immediately reveals this data quality issue. The next ones, the three at the bottom, these seem to be really false positives. And here you can see again this welcome appearing. And then it seemed that websites where you have search functionality, as you sometimes have on travel websites, or in this case, investment fund websites with some search functionality, the model has wrongly learned that it's then adult content. And so this immediately reveals that in your data set, there probably is a bias that you have very few websites with the search component that are non-adult content. And so this reveals, well, add more of these kind of investment websites with search functionality, label them as non-adult content, and that will improve the performance of the model. So recently we have proposed a counterfactual generating method for images as well. And we applied this to explain misclassifications. And so we used the Google model on ImageNet. And we saw that many images of lighthouses were wrongly predicted as being that of a missile, of a rocket. And so here you can see images of missiles. And we were like, why is this happening? Let's try to explain these misclassifications and see what the reason is. And so here, for example, you see an image from ImageNet that's misclassified as a missile. And we were thinking, why would this be? So if you don't have an explanation, now comes the guessing part. Well, maybe it's because of the shape. It's kind of like a missile. Maybe it's because it's horizontal, and all these images of missiles are horizontal, and that's why the deep learning might have think it's a missile. Well, the counterfactual explanation, which is shown in the middle, reveals that actually it's clouds in the background. Clouds that resemble the shape of exhaust plumes that you often have behind missiles. So here you can see very often these images of missiles have this huge exhaust plume behind them. And here you can see in the background, indeed, you have clouds that have this shape like an exhaust plume. And so it turns out if you remove this, and in image classification, removing corresponds to blurring. If you would blur that part, well, now the classification becomes correct. It becomes beacon or lighthouse. So now it's correct. So this really reveals what's going wrong in the image. And so if your Tesla is running into a white truck because the prediction was a cloud, well, now you have a tool to say, well, why is this happening? Why did the neural network think it was a cloud and not a white truck? And then moving to the other kind of decisions you want to explain, unfair decisions. And looking into this area, it's an even bigger mess. So how to assess fairness, it's just crazy. There's so many measures out there. They're proven to be mathematically incompatible. Some of these measures where only if you have, for example, a model that's perfectly fair, perfectly correct, sorry, makes perfect predictions always, then certain metrics are compatible. So these metrics to assess how fair your prediction model is, in the sense that it's not discriminating against a sensitive group, are really very all over the place. There are hundreds of them out there, and it's really not clear which one to use. And now recently, there's been a call for actually we shouldn't rely on these fairness metrics. What we should have is research that opens up why models are making seemingly unfair decisions. And then there should be a transparent discussion of, do we think it's fair that the model is making these decisions or not? But we shouldn't rely on a single metric to assess whether a model is fair or not. And so I think one of the main researchers making this claim is Sandra Wachter from Oxford University. A really interesting paper who really focuses specifically on that part. And so we try to answer that call by merging counterfactuals in the fairness research. And so we say, well, let's look at counterfactual explanations of negative decisions. For example, being rejected for a job offer. And then we want to see, is this model discriminating against women, for example? And then we say, well, let's look at all the explanations for rejected women. Let's look at all the explanations for rejected men. And let's see what features occur more with women than for men. And for example, we might see, well, height, how tall you are, occurs much more often in counterfactual explanations of rejected women than for rejected men. And then the idea is that this should spur a discussion of the people using the model, making the model. Is that justified, yes or no? Well, height is important. If you're a fireman, certain tools are only built for people from a certain height. So yes, it's justified that in this case, we're discriminating against women because of this reason of height. That's justified, might be a reason. And so we formalize this, we optimize this, and then we apply to a bunch of data sets. For example, the adult income data set. And so with the adult income data set, you try to predict whether somebody will make more than $50,000 or not. And so the positive outcome is being rich. You'll make much money, or vice versa, not being rich. And then the sensitive attribute is your gender. And so we did exactly that. We built a random forest model. We looked at the counterfactual explanations of women that were predicted to have a low income, the same for men that are predicted to have a low income, and then we compare the counterfactual explanations, the most occurring features. And then the first thing we look at explicit bias. So suppose the sensitive attribute is really included in your model. And then we say, well, let's look at counterfactuals in the form, if your gender would be man instead of woman, then your prediction would change from negative to positive. And we found that actually, if you have the gender in your model, this kind of explanation occurs 13 times for women, while it occurs only once for a man, where it's stated if your gender would change from man to woman, then your class would change from negative to positive. So this already indicates if you would include the sensitive attributes, you seemingly have a big issue. Gender is really being used to discriminate on whether you have high or low income. But in most cases, you don't have sensitive attribute in your model. And that's where then you look at how often do you have explanations with a certain feature in it for negative outcome. And then we see the feature most occurring for women with a negative outcome much more often than men with a negative outcome is marital status. And so the explanation that's provided much more for women than for men is, if your marital status would change from married, would change to married to a civilian spouse, then your prediction would change from negative to positive. And on the right, you can see married to civilian spouse, it's value 2. And you see that occurs in your data set much more often for men than for women. So you see, it's kind of a proxy for gender. And then it's up to, again, whoever's using this model to decide, is this justifiable? Is it okay that the model is thinking, mainly because you're not married to civilian spouse? That's the reason why we give women much more often a negative prediction than for men. Is this justified, yes or no? One might argue no, because it's because of historical bias in the data set. This is not justifiable. Then you could see, what should we do about it? And so this really explains it. Here, another data set from Catalonia data set, where we try to predict, will somebody recommit a crime, so recidivism or not? And so the negative outcome is predicting somebody will reoffend a crime. And we want to see whether this model is discriminating based on nationality, if you're a foreigner or not. Well, with explicit bias, if being a foreigner is part of your model, well, we actually find that of 28 foreigners with a negative outcome, actually 7 times a lot, really, 25%. The counterfactual explanation would be, well, if you would not be a foreigner but a local, then we would predict you would not reoffend. Clearly discriminating. But as I said before, implicit bias is most interesting. And then we see, well, there's another attribute, national group. And it comes with, for most of the negative outcomes of this sensitive group, it comes with counterfactuals like, if your national group would have been Spanish, then your prediction would change from negative to positive. And here you can see on the right, national group. Well, of course, for all local people, it's always Spanish, and for all foreigners, it's something else. And again, you see here clearly it's just a proxy of being a foreigner or not. And then it's up to whoever uses it to say, is it justified or not to do this? And then you see the second variable, crime type. The type of crime apparently also is much more different, the counterfactual explanations, for foreigners than for non-foreigners. So you could investigate that further as well. I'll leave it at that. We also did it for student performance data sets where the most often counterfactual explanation for girls and to predict whether you would do good or not was actually the school you would go to. And so it's counterfactual would be if your school would have been some other school, then your prediction would change to a positive outcome. And the most occurring is GP. So for a girl, if your school would be GP, then you would predict to have a high score. And then you see GP, it's mainly boys going there. So it's really exactly what happened in the UK with the A levels. For those who know the story with COVID happening, they couldn't do the test. And so they built a prediction model and it was based on the school. And so exactly this, what's revealed here, was a whole issue there where it's based on school. But so for some schools, as an individual, you do really well, but actually the whole school does much worse because of some bias in the data set. The same with law admission, where LSAT turns out to be occurring most often, and so on. And so this metric sheds light on what attributes would have led to a different outcome. And so this can really jumpstart a discussion to see whether this really is because of historical inequality that are present in your data set, or is it really justified discriminators. And remember again that you cannot do this with feature importance methods, because you want to see when the decision changes, not simply why a certain prediction score happens. And so you really need explaining decisions for an individual instance, and then automatically you come to counterfactuals. And this really is a human in the loop, which I'm really, really start to believe. You cannot automate all of this. You can automate as much as possible, but you really need this human in the loop where in the end, you do not automate everything. You just give this kind of decision support system to people to understand, is this model being fair or not, and should we be using it? So explanations, counterfactual explanations, are really useful to explain incorrect decisions or unfair decisions. And that's something that simply these feature importance methods are not doing. And so to conclude, explainable AI, don't dismiss comprehensible AI too easily. Sometimes simpler is really better. Beware of researchers like myself who always suggest new algorithms of explainable AI. Sometimes you don't need it. And there's plenty of research to do in this area. So I want to conclude with this story again. Now imagine a world where Apple Card Goldman Sachs was using counterfactual explanations. Well, perhaps the Apple Card would have responded, well, if your wife would have also had 20+ years relationship with our bank and would have been regarded as a premium customer at some point in time, then she would also have received a 20-time credit limit. And then this guy might have said, okay, now I understand. It's not sexist. It makes sense. Thank you for the additional feedback. Or potentially it would say, well, if your wife's relationship status would have been husband instead of wife, she would also receive this high credit limit. We clearly messed up. We're updating our models as we speak. And then perhaps Stephen Wozniak would say, Thank you for this reaction, and to react responsibly. It's how big tech should be in the 21st century. And with that, I conclude. I'm open for any questions that you might have. And here, a short marketing for my book that just came out last week.
Thank you so much, David. It has been a really inspiring talk, and the floor is open for questions from the audience. So if you would like to pose a question, please raise your hand, and we will give you right to the microphone and the camera. So Janice would like to question, and of course you are getting a lot of excellent talk comments on the chat. I can tell you that too. So Janice, please go ahead with your question, and thank you very much for coming today.
Yes, hello. Thank you very much for this nice talk. I was just curious, is the idea of this counterfactual, or this counterfactual idea of finding the minimum number of attributes, for example, is this the same like finding adversarial examples? So if you would, for example, use the zero norm and finding the closest point which makes your model fail somehow.
Yeah, very good point. And so indeed, adversarial thinking is quite similar in the sense that you also want to see what needs to change in order to come to another classification. The main difference is that you need semantics in a counterfactual explanation. And so one of the most well-known examples of adversarial learning is you add some random noise, intelligent noise to an image, and suddenly the classification changes to something completely different. Here, an explanation that's noise is not allowed, because you really want semantics. You want to have an explanation that's understandable. And so because of this, the whole optimization routines are completely different. So we also looked at, can we actually use this adversarial learning for counterfactual learning? But the optimization goal is very, very different. And because of that, there's a divide in the research that's happening in these two areas, actually, even though, as you correctly articulate, the goal itself seems to be quite similar.
Okay, thank you.
Thank you very much, Janice. Emilio, would you like to pose your question? So Emilio Gamba would like to pose a question. Otherwise, I can read it. So Emilio says, how do you know if a user is able to understand the explanation?
Yeah, terrific question. And I think it's one of the big issues with computer scientists doing this kind of research, that it's all based on algorithms, and then we find some metrics. And so the field is a bit moving towards doing more user studies, because exactly what you say, how do you know whether it's actually understandable by a user? So the main thing we're currently doing is just enforcing it has to be, for example, a small explanation, or enforcing that the explanation must have semantics, like what words are present in the website, where if you would remove it. So it's a set of words. In this image, we first cluster the image, and then we say what clusters need to be removed in order to come to an explanation. So we enforce that there's semantics, that it's understandable to a user, because otherwise you might have these adversarial learning kind of approaches. We just have noise, which is totally not understandable to an end user at all. And so we try to do that kind of research too, where, for example, we looked at, do people find counterfactuals more understandable than, for example, feature importance methods? Because we can claim this, but is it actually the case? And what we see that it really depends on the application, on the level of how advanced in math that people are, in what their background is, even in explainable AI and so on. So I think this in itself is a real interesting area to work on this human-computer interaction. What do people actually want, under what application, under what circumstances? And I think we probably need to do that first before we can, and then start building more algorithms to tune for that. And so we just came up with the idea it should always give a counterfactual. But that's something we say. And then there's some domain experts that, of course, iterate that. But I think it would be better if the domain experts or field studies come up with, well, these are the criteria we have, and then build more algorithms that are tailored specifically towards these criteria. So lots to say about this this question, because indeed it's a very important one.
Thank you very much, Emilio. Is there any other question from the audience? So Manuel is asking, do you know if anyone, sorry, I've lost the question, has applied this to optimization?
As applied this to optimization. Well, first, if the question is optimization used to get this, well, yes, all of them are using some optimization routine, but apply this to some optimization.
Yeah, I think that's what Manuel wrote. Yeah. So you find a counterfactual for an optimization model.
Yeah. So it goes, as far as I know, it's typically always used within prediction models, making so classification mainly, making a decision. So if you have, if I understand correctly, some optimization where you have some final decision happening, then this could be could be used as well. I haven't seen that happen.
Yeah, he was asking for feasibility analysis, for instance, but yeah.
Yeah, I haven't seen that, to be honest.
Okay.
Yeah,
thank you, Manuel, for the question. Is there any other question from the audience? Well, David, it has been an amazing talk. We thank you very much for bringing all these new ideas. And thank you again to the audience for coming today and for being active in this Q&A session. So we see you next week. And to David, hopefully we see you at some point in a conference very soon. Thank you very much.
Great, thank you.